Hey guys, today we're going to do an inverse review, okay? So kind of looking at graphs, their tables, functions, just all of it, all right? So first, inverse, that's when you switch the x and the y values. So this rule can be applied to any situation when you have an x and a y. So given this table right here, we're going to write the table for the inverse functions. So the inverse function of this table, I just switch the x and y values. So instead of the coordinate point -1, 4, it becomes 4, -1. Instead of 0, 7, it becomes 7, 0. And instead of 1, 11, it becomes 11, 1. And that's it. Okay? That's the table of the inverse. All right, to find the inverse of this relation, again, we're just going to switch the x and the y. So it's going to look like this. If I can draw the little bracket guy, there we go. Instead of -5, 7, this will be 5, or I'm sorry, 7, -5, whoops, like that. Then we'll have -8, -6, just switching those. Then I have -2, 1, and I have 3, 10. And that's it. Okay, just switching the x and y's. All right, number 3 says, draw the inverse of this graph on the same coordinate plane. So we're given this graph right here. I'm going to pick a couple values. I'm going to pick these coordinate points, and I'm going to switch their x and y values, okay? Just like we've learned so far. So this is -2, 4, so it's going to become 4, -2. And this was 0, 3, so this becomes 3, 0. This is 2, 2, so that would still stay 2, 2. All right, let's do this one. 4, 1 becomes 1, 4. So this is what the inverse function looks like. Okay? Now it says describes how you can transform the original graph onto the inverse. So all we did was we switched the x and the y values, right? However, notice that this black line and this red line, they are symmetric. They are symmetric with the line y equals x. Do you guys see how this piece is this piece of this function, and this piece becomes this piece if we reflect it? Okay, so this piece reflected over this dotted line is here, this piece is here. Okay, so I just want you guys to also note right here that the original graph and the inverse, they are symmetric with the line y equals x. Okay? All right, number 4. F of x is solid and g of x is dotted. Are they inverses? Yes or no? If yes, explain why. So looking right here, f of x, and this is g of x. So let's just look at a few of their coordinate points, or we can look to see if it's symmetric with the line y equals x. So I'm going to draw the line y equals x in here. And it looks like this piece is reflected right here, and it looks like this piece is symmetric right here too. But let's look at a couple coordinate points. So this is -5, 4, so this would have to be 4, -5, which that matches up nicely. All right, let's check another one though, because we can't just assume, right? Let's see here. It looks like we have -4, 0, so that would be 0, -4. Yep, that matches. Let's do one more. Let's do this one. -1, -6, it looks like. So -6, -1. Yep, all of those work. So are they inverses? Yes. And you can say that they're symmetric with the line y equals x, or you could say that the x and y values are switched. Okay? All right, let's look at this graph over here. Let's draw in the line y equals x. Ooh, that does not look like it's this solid line is symmetric with the dotted line, so we can just already say no, not symmetric with y equals x. Or you could even look at coordinate points and show that they're, when you switch the x and y values, it doesn't equal what's on the dashed line. Okay? All right, flip it over. All right, a relation is a function if every input has only one output, okay? This means that every x value is paired up with only one y value, all right? Another way to tell if a function, or if a table set or a graph is a function is the vertical line test. Any vertical line drawn on the graph can intersect the graph one time. I'll show you guys what I mean by that. So if it passes the vertical line test, it's a function. If it fails the vertical line test, it is not a function. So we're going to take a look here. It says, are these relations functions? And explain why. All right. So looking at this function number 5, or this relation number 5, each input has exactly one output. So this x value has one output. 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 And this function has one output. So yes, this is a function, and it's because each x is with only one y. So even though these x's both go to 1, it's okay. You just can't have like -4 going to 2 different y's. All right, so just be careful though there. So you can say yes because each x is with one y. All right, number 6. We got 2, 6, 5, 7, 6, 9, and 6, 10. Woo. 6 goes to 9 and to 10. So remember, a relation is a function if every input has only one output, okay? The number 6 has 2 outputs, so this is not a function. X equals 6 has 2 outputs. It equals 6 and 10. Or I'm sorry, 9 and 10, not 6. Whew. Alrighty, number 7. So instead of like looking at the table of values, you could just use the vertical line test. In the vertical line test, you can just use your pencil and go, it's up and down, vertical, right? And just go like this. Now, if the function goes through your pencil more than once, then it fails the vertical line test. It can only go through your pencil one time. So here, the function goes through my pencil once, one time, one time, one time, one time, one time, one time. Okay, yes. This is a function. This passes the vertical line test. Number 8, vertical line test. Going through, going through. Uh-oh. You see how the function goes through my pencil 2 times? Right here, right here, and right here, right here, right here, right here, right here, right here, and so on. So this is not a function. It fails the vertical line test. Okay? The horizontal line test, I'm going to use HLT for that, since we use VLT for the vertical line test, is used to determine if your inverse is a function. Okay? So is the inverse of each a function, y or y not? Sorry, I don't know why that took me so long to comprehend right there. But, okay, so horizontal line test, it's going to go this way, right? This is horizontal. So looking at this graph, if I put my pencil through it, it only crosses through, the function only crosses, or the, well, yes, it is a function. The function only passes through my pencil one time and at each y value. So this is the inverse is a function because it passes the horizontal line test. Over here, number 10. I'm going here, nope, nope. See how I'm going through my line, or my pencil twice here, and here, and here, all the way up here. So this would be, the inverse is not a function because it fails the horizontal line test. So make sure you're paying attention to the directions. This is just asking If this is a function, you use the vertical line test. If you're asked to determine if the inverse is a function, then you use the horizontal line test. So horizontal line test is for the inverse function. Okay. All right. The symbol for inverse of f of x is f to the negative first of x. Okay. So now we're going to solve these algebraically. So it says find the inverse of each algebraically, label the inverse with the correct notation. I put the steps over here off to the right hand side. First we're going to change f of x to y, we're going to switch x and y, and then we're going to solve for y. Okay, so step 1, change f of x to y. And just like we learned like inverse functions, you can just switch the x and y values, so that's what we're going to do, switch x and y. Notice I didn't move the 3 with the x. You're just changing the variable. Okay? And then now we're going to solve for y. So I'm going to add 1 to both sides. So x plus 1 equals 3y. And I'm going to divide everything by 3. So this will become 1/3 x plus 1/3 equals y. But I want you to label the inverse with the correct notation. So we're going to say f of negative 1 to the x is 1/3 x plus 1/3. Okay? All right, number 12. Change f of x to y. Switch x and y. Solve for y. I'm going to add 5 to both sides. So x plus 5 equals y squared. To get y by itself, I'm going to take the square root to cancel out that 2. So I get y equals square root of x plus 5, but we want to use good notation. So f to the negative first of x equals the square root of x plus 5. Sorry that my hair's getting in it. All right, number 13. Change f of x to y. Switch x and y. Solve for y. So I'm going to subtract 3 first, because this is where the y term is, so x minus 3 equals 1/2 y. Now to get rid of that 1/2, okay, yes, you can divide by 1/2, but when you're doing that, you're really just multiplying both sides by 2. So you get 2 times x minus 3 equals y, because those will undo each other. And then the correct notation, f to the negative 1 of x equals, I'm going to go ahead and distribute this 2. So I get 2x minus 6. All right, last question here. So you guys do not need to distribute that if you don't want to yet. Okay, you guys can leave it like that. But let's change our f of x to y. Switch x and y. Now we're going to solve for y. You guys could distribute this if you want. If you did that up here, and then you switch x and y, you would get the exact same thing. So I'm going to add 8 to both sides. And then I'm going to divide both sides by 4. If you like to just divide each term by 4 rather than like writing the whole thing divided by the 4 on this problem, that's fine. I kind of did this whole thing by 3 over here, but if you want to do each individual piece, that's fine too. So you get y equals 1/4 x, because there's a 1 right there, plus 8 divided by 4 is 2. So f to the negative first of x equals 1/4 of x plus 2. And that's it. Go ahead and try your homework out. See ya!